In the previous lectures, we have seen different examples of minimization of DFA, and in this lecture, we will be seeing another example of minimization of DFA when there are unreachable states involved. Okay, so before we start, let us try to understand what is an unreachable state. A state is said to be unreachable if there is no way it can be reached from the initial state. Okay, so in the DFA that we have here, we see that F is called an unreachable state. And why is F an unreachable state? That is because there is no way in which F can be reached from the initial state. So here we have our initial state as A, and if you observe carefully, you see that there is no way in which you can reach F from this initial state A. And there is another way in which you can easily identify an unreachable state, and that is unreachable states will only have outgoing transitions and will not have incoming transitions. So if you observe here, you see that the state F has outgoing transitions for 0 and for 1, but there are no incoming transitions. That means nothing comes into this F, only outgoing transitions are there. So that is how you can easily identify an unreachable state. Now let us see how we can minimize a DFA when there are unreachable states involved. The procedure is very simple. Whenever you have an unreachable state in your DFA and you need to minimize it, the first thing you have to do is just remove that unreachable state from your DFA and then proceed as you normally would do. So here in this DFA, let me remove this unreachable state F and draw the transition table for this DFA without the unreachable state F. So here I have now removed the unreachable state F, and then I have made the transition table without the unreachable state F. So here A is my initial state, and we have three final state here, B, C, and G. B, C, and G, and this is the transition table. Now the procedure for minimizing is same like we used to do. So let us write the equivalences for this. Starting with the zero equivalence, how do we write the zero equivalence? We put the final states and non-final states in separate sets. So here what are my non-final states? They are A, D, and E. And what are my final states? My final states are B, C, and G. So that is how we write the zero equivalence. And one equivalence, I'm not going to solve it step by step because I've already explained in the previous lectures. So if you solve it, you will find that in one equivalence you will get states A, D, and E, which are one equivalent to each other, and then you'll find that states B and C are one equivalent to each other, and G is not one equivalent to any of the states. And if you solve for two equivalents, you will find that state A is not two equivalent to any of the states, and states D and E are two equivalent to each other, and state B and C are two equivalent to each other, and G is by itself. And in three equivalents, if you solve it, you'll find that state A is not three equivalent to any of them, and states D and E are three equivalent to each other, and states B and C are three equivalent to each other, and state G is by itself not three equivalent to any of them. So if you observe carefully, you can find that the rows of two equivalents and three equivalents yield the same result. So since they are same, it's time to stop the procedures, and these are the states that I have to make in my minimized DFA. So let me draw the transition table for the new minimized DFA over here. So here I have my transition table for the new minimized DFA, where I have states A, D, E, B, C, and G, like it is given here. And A was the initial state in the original DFA, so A is the initial state even in this one. And in the original DFA, B, C, and G were final state. So here state BC is final state and G is also final state. Okay, so let us fill up this table. A on getting input 0, where does it go? It goes to B. So instead of B, what should we write? We should write BC. We'll write BC. And on input 1, where does it go? It goes to C. Instead of C also, we have to write BC because C is contained in BC. And in the same way, DE on input 0, it goes to state G. And on input 1 also, it goes to state G. And BC on input 0, it goes to DE. And on input 1 also, it goes to DE. Okay, and state G on input 0 it goes to G itself, and on input 1 also it goes to G itself. Okay, so here we have completed the transition table, and now let me draw the transition diagram. So here we have A as my initial state or starting state, and then we have another state called BC. BC is another state, and let us know that BC is the final state, so I put two circles around it. And another state that I have is DE. DE is another state, and another state I have is G, and G is also final state, so I have to put two circles around G. And A, on getting input 0 and 1, it goes to BC. On both input 0 and 1 it goes to BC, and BC on input 0 and 1 it goes to DE. So BC goes to DE on both inputs 0 and 1, and DE goes to state G on 0, and also on 1 it goes to state G. So DE goes to G on inputs 0 and 1. And what about state G? G on getting input 0 and 1, it stays in G itself. So G stays in G itself on getting inputs 0 or 1. So here we have completed the state transition diagram for the new minimized DFA that we have obtained. So in the original DFA, how many states we had? We had 1, 2, 3, 4, 5, 6. 6 states. And if you count the unreachable state, it would have been 7 states. But in the minimized DFA, we have only 1, 2, 3, 4 states. So here we have successfully minimized the given DFA even when there was a unreachable state by removing